speaker today is Christopher Mauger. Christopher is a senior scientist at Los Alamos National Laboratory. He is, I guess the two hats that you wear right now is that you are a project manager for the DUNE detector for the so-called Deep Underground Neutrino Experiment, or DUNE. And also he is the spokesperson of an experiment called Captain, which I don't know if we're going to talk about that today.
A little bit.
And which is an ongoing neutrino experiment to measure a special kind of detector called a liquid argon time projection chamber in neutron and neutrino beams, both at Los Alamos and Fermilab. So he actually came from, I guess the last time, we actually worked together when you were a graduate student. So I always think of you as a graduate student. He got his PhD in 2002 from at Stony Brook, working, I think it was the K2K, the world's first long baseline neutrino experiment. And from there he went to Caltech, where he worked, a person that some of you may know, Bob McEwen, who's now the science director of JLab. And he was working on an experiment in Japan called CAMLAB, which made him the first real definitive measurements of an actual neutrino oscillation versus just neutrinos disappearing. And so now he's he then went off to Los Alamos, and he's been there working both on Captain and on the DUNE project. So without any further ado.
Okay, thanks very much, and thanks a lot for the invitation. Nice to see a full room for this discussion. So I'm going to talk about neutrino physics for the most part, and in particular about neutrino oscillation physics, some of the experiments that have been done over the last several years that have given us some insight into neutrino oscillation physics, and then spend time focused on this future experiment called DUNE, the Deep Underground Neutrino Experiment, and what we may accomplish with it. So again, I'll introduce neutrinos and mention the standard obligatory slide on the standard model of particle physics, talk a little bit about neutrino oscillations, and then discuss sources of neutrinos and neutrino measurements, discuss this program that we're building and planning now, as well as some of the scientific issues that require some other measurements to be made in order to extract the best physics from the DUNE. So why do neutrinos exist? And they're quite mysterious. They even disappear from the board. They were first postulated actually to maintain an idea that physicists hold quite dear, which is the idea of energy conservation. Back in the early part of the 20th century, various forms of radioactive decay, alpha, which were labeled alpha, beta, and gamma, were found in alpha decay. And in gamma decay, the alpha particles and gamma particles came out with definite energies, whereas with beta decay, the beta particle was emitted with a spectrum of energies. And besides the recoil nucleus, there were no other visible particles. And this was something of a conundrum, and so Wolfgang Pauli postulated that in fact there actually is a third particle. But this particle, because it's not seen, has to be very light, and it has to be neutrally charged. And so this is the origin of neutrinos. It took 25 years after they were first postulated before Reines and Cohen actually discovered for the first time and measured neutrinos. And so with a third particle, that then explains why there's a distribution of betas in radioactive decay. It also turns out we've learned a lot about neutrinos since then, and we now understand that in fact in the universe there's a similar number of neutrinos as there are photons throughout the universe. So the standard model is divided into fermions, considered the matter particles, and bosons, which are carriers of force. And so there are two types of two classes of these particles. There's the quarks that feel the strong electromagnetic and weak forces, and then there are the leptons, which don't feel the strong interaction. And these are divided between those that are charged, which include the electron, for example, and those that are not charged, these neutrinos. So for each generation, for each of lepton, there is a partner neutrino. And in fact, what we find experimentally is that in general, the total lepton number is actually a conserved quantity. And so for electromagnetic interactions, these are represented by the exchange of a photon. For strong interactions, the exchange of a gluon, and for weak interactions, the exchange of either a Z boson or a W boson. And importantly, in the standard model, neutrinos are actually massless. And so massive neutrinos on their own imply physics beyond the standard model. And so one can then ask, well, what are the consequences if neutrinos have mass? Can we actually find a place where this is actually visible? And so, for example, one can look out into the universe, and this is a very old calculation, but it's quite a stark calculation. So for illustrative purposes, it seemed interesting to show that in fact, if neutrinos are massive but still relativistic, they actually can carry away energy density, or in fact, because they have a large energy density, they create a larger expansion rate in the universe, and this inhibits structure on small scales. So you can see for a relatively large neutrino mass versus structure for relatively small neutrino masses in simulation. So ways to actually search for neutrino mass. One can search again for the impact of massive neutrinos on large-scale structure, and there are people in this room that are involved in experiments that do just that. One can also search for kinematic effects in the beta decay, in some beta decay spectrum near the endpoint, and that's what's represented in this graph right here, that if the neutrino mass is truly zero, of course, and you measure the energy spectrum of the beta particle very close to its endpoint, you should get one answer, and if the neutrinos have a finite mass, that should actually kinematically impact the shape of this beta spectrum, especially near the endpoint. And then finally, and what I'm going to spend most of the time talking about, is looking for the phenomenon of neutrino oscillations. So, what are neutrino oscillations? Well, if we assume that there are massive neutrinos, we know that neutrinos are created in weak interactions. And so when they're created in a flavor eigenstate, that is an eigenstate of the weak interaction. So either electron, muon, or tau. But if they're propagating in time, of course, they propagate actually according to the masses that they have. So you can write this flavor eigenstate as a sum of mass eigenstates, again for each possible active flavor that we know about, and you would have, for example, the same number of mass eigenstates labeled with I here for I equal 1 to 3. And so if the neutrino actually propagates with the free particle Hamiltonian, then one has some type of expression like this, and this Hamiltonian, of course, is really dependent on the energy of the neutrino, which is correlated with its mass rather than with its flavor. And so one can then go through and calculate the survival probability. If you create a neutrino in a weak interaction in one flavor, this survival probability is after some time, is the neutrino still in that flavor eigenstate, or has that flavor eigenstate changed? And it's nice to look at the two-flavor case. It's a little bit easier to understand. And there's some important features in this two-flavor case that are also true in the full three-flavor calculation. So here, if we imagine the universe only has electron-type and muon-type neutrinos, and they're related to two mass eigenstates like this, one can then go through and calculate the survival probability if one makes, for example, an electron neutrino. What's the probability that at some time later it's still an electron neutrino? And one comes up with an expression like this. There's a term that's proportional to this mixing angle, and then there's another term here, and this term depends on several things. It depends on the mass splitting, so this delta m squared is m2 squared minus m1 squared. So one thing to note is this delta m squared actually can have a sign. If you could measure delta m squared directly, you could actually tell which mass eigenstate were heavier than the other. But you'll also notice that in this two-flavor case and in the vacuum approximation, that in fact you cannot, by measuring neutrino oscillations, tell the sign of this delta m squared because it's stuck inside a sine squared. You also see a parameter L over E. And this is a very important parameter in neutrino oscillation physics. And the L comes from time, and that's because we're working here in the ultra-relativistic approximation. So L would be the distance from the production point to the point at which neutrinos are detected, and E is the neutrino energy. And so this factor of 1.27 is what happens to H bars and to C's when you want to express these values in important, in very useful quantities. So for example, delta m squared is expressed as EV squared. L is the distance, again, from the production point to the measurement point. E is the energy of the neutrino, and if you express L in kilometers, then you can express neutrino energy in GeV, or equivalently, if L is in meters, then E is in MeV. And so you can ask the question, well, then what do we measure in experiments? And so basically there's some kind of neutrino source, there's some distance L, and then there's a neutrino detector where we make our measurements. And so in experiments in general, we control L and we control E. And of course, nature gives us the mixing angle, and it gives us the differences of the squared masses. So we can fix L or E, or we can have a spectrum of L's and E's. And this gives us the lever arm to go forward and try to measure this mass splitting and measure the mixing angle. There's another very important effect, which is what happens when neutrinos traverse matter. So you can imagine that we use the free particle Hamiltonian in what we derived so far. But if the neutrinos are passing through matter, they also will feel the potential V from the matter through which they're traversing. And so since the phenomenon of neutrino oscillations is due to phase differences between the flavors, V only impacts their survival, or the disappearance or the appearance probabilities, if it actually generates a phase difference. And so the question is, well, when can some kind of matter potential actually generate a significant phase difference? And that's when the interaction modes between flavors differ. So for example, regular matter has electrons, right? It's made up of atoms, and so there are many, many electrons. In general, it's not made up of atoms composed of mu's or tau's. And so we expect that there'll be a potential difference between electron neutrinos and the other two types of active flavor of neutrinos, muons and tau neutrinos, but we would expect that there would not be a difference between muon and tau neutrinos. Furthermore, because matter consists of matter rather than some equal admixture of matter and antimatter, we also expect differences between the appearance probabilities or the survival probabilities of when we're comparing neutrinos with antineutrinos. So we have these two cases. We have vacuum oscillations, and so in a two-flavor approximation, this is the relevant survival probability. And here you can see that you can only measure the magnitude of the mass splitting, again, because this mass splitting is sitting inside this sine squared. Whereas in matter, things get a little bit more complicated. And this is a particular calculation that's relevant for the solar neutrino problem. But you can see here that this delta m squared is now not sitting inside this sine squared, and is in fact exposed. And so by measuring these probabilities carefully, one can actually distinguish the sign of the mass split. So I'd like to go through a few examples of neutrino oscillation experiments. And my favorite one to show is the first full detector that I got to help build back many years ago together with Bob and others. And it's always nice to show because it's such a beautiful detector. So these are actually human beings who are actually cleaning up the surface of these very large photomultiplier tubes. The diameter of each one of these photomultiplier tubes is 20 inches, so it's about this big. So this is an enormous detector, 40 meters in height and 40 meters in diameter. And it's true that neutrino physics really employs the largest particle physics detectors that are constructed by our species. So there are 13,000 photomultiplier tubes in a 50 kiloton water tank, and that gives us 22.5 kilotons of fiducial mass. The PMTs detect Cherenkov light from outgoing charged particles and neutrino interactions, and the detector is actually in a mountain to shield it from cosmic rays. So above this detector is about 1,000 meters of rock, and one of the units that we like to use in big underground experiments is the meters of water equivalent, and that's about 2,700 meters of equivalent mass in water. So what is Cherenkov radiation? When a charged particle is actually traveling faster than the speed of light in that particular medium, right? The limitation on charged particles is that they can't go faster than the speed of light in vacuum. But the speed of light in a medium will be lower than that. It induces an optical analog to a sonic boom. And it creates a cone of light that's emitted at a characteristic angle, while that particle is significantly above something called the Cherenkov threshold. And so it turns out that these particles can create these characteristic rings at a very particular angle. And so, for example, for heavier particles like muons, one has a very, very sharp edge to the ring. So for non-showering events, that is events where the traveling charged particle is much heavier than the electrons in the medium, one has a very, very sharp ring. Whereas for electrons and showering particles, one creates a much more fuzzy ring. So one can actually do pattern recognition and distinguish between non-showering and showering events. And so in these detectors, events that come from charged current electron neutrino type interactions will create showering events, and events that come from charged current muons, muon neutrinos, will create non-showering events. And so if one's doing an oscillation experiment, one starts with a muon neutrino beam, one can then look for example, electron appearance by looking for these two different types of rings. And the amount of charge, and that is the amount of light that's in this ring, is basically proportional to the momentum of the particle. So in this rather awful cartoon, we can hopefully learn about where the atmospheric neutrino flux comes from. So this is a model, not to scale, of the Earth, and this is the Super Kamiokande detector that's of course very close to the surface of the Earth. But there are primary cosmic rays, many protons in particular, that impinge on the Earth isotropically. And these cosmic rays interact with, nuclei in the upper atmosphere, and they create showers of hadronic particles, in particular a lot of charged pions. And charged pions, which would be the secondaries here, subsequently decay to a muon and a muon-type neutrino. And this muon often subsequently decays and gives us an electron, a muon-18 neutrino, and an electron neutrino. And so by looking at this very simplistic diagram, we see that this ratio of muon-type events to electron-type events is roughly 2. And also because the primary spectrum of cosmic rays is basically isotropic, without neutrino oscillations, one would expect that the flux of atmospheric neutrinos and the flavor ratio as a function of neutrino energy of atmospheric neutrinos should be the same for atmospheric neutrinos that are very close to where the detector is versus those that are produced 13,000 kilometers away on the other side of the Earth. So Super Kamiokande in 1998 announced results of this measurement that showed that actually there's a significant asymmetry, particularly in the muon-type events. And so if you look along this axis, these are the electron-type events. This is the zenith angle. So -1 are for events that are upgoing, that is those that were made 13,000 kilometers away from the detector, and those here are made directly overhead, about 13 kilometers away. And so in the muon-type events, you start to see a very large deficit for neutrinos that were made on the other side of the Earth. And this was really the first really solid evidence for neutrino oscillation physics. And this has been interpreted as evidence for muon-type neutrino to tau-type neutrino oscillations. So the first results were announced in '98. This is from a later paper. And in fact, these neutrino oscillations have been confirmed by the Decay and the Minos-long baseline neutrino experiments. And then you can see a typical diagram in a neutrino oscillation experiment that has the mass splitting, the magnitude of the mass splitting on one axis, and the mixing angle on the other. So solar neutrinos have also been measured. Many experiments, including Super Kamiokande, and really culminating with the SNOW experiment, have measured solar neutrinos with a deficit that was first noticed by Ray Davis, even I think as early as the late 1960s. And because of the very neutrinos are made in the core of the sun, which has a very high density, and the density of the sun gradually changes as you get out to the very edge of the sun, from being significantly more dense than the Earth and significantly less dense than the Earth. And because of that matter distribution, matter effects are actually quite important. So not only did these experiments find evidence for oscillation, but they actually could make very nice measurements and understand the mass splittings as well. And not just the magnitude, but the sign of the mass splitting. Solar neutrino oscillations were further explored by reactor neutrino experiments, and in particular by the Camland experiment. Reactors are prolific sources of electron antineutrinos. So the Camland experiment was located in the same mine as Super Kamiokande, and at the time, Japan produced a very large fraction of its electric power by nuclear reactors that you can see distributed across the country. And so Camland was at a very fortunate location to actually measure reactor neutrinos, because it was looking at the same L/E regime that was of interest to due to the results from the solar neutrino experiments. One other important difference between Camland and Super K is Camland, though smaller, uses scintillation rather than Cherenkov light like Super K, and so there's a much higher light yield and a much lower energy threshold. And so this is just a diagram of that detector underground, as well as its location inside Mount Ikinoyama. And so the Camland scintillator was sitting in a very large containment vessel. This vessel is a very, very thin, essentially tri-layer piece of plastic, about 135 microns thick. It's surrounded by buffer oil and a lot of photomultiplier tubes. And this was used to make the scintillation measurements of the inverse beta decay process.
How does the neutrino flux there compare to solar neutrino flux?
Let's see. The flux is actually lower, but the cross section is significantly higher. So the inverse beta decay cross section turns out to be much higher than the elastic scattering cross section that Super K measures, for example, from the solar neutrino flux in the same location. So that's roughly the issue. So the Camland event rate, for example, was roughly a few per week, and that's in about a kiloton. The Super K event rate for solar neutrinos was about 22 per day in 22.5 kilotons. So,
Thanks.
above a particular threshold, I mean. The absolute flux of solar neutrinos, so the solar neutrinos measured by Super K are actually way out on the tail of the spectrum here. This is a log scale here. So Super K is looking at mostly the boron 8 spectrum, and from about here and above. This here that's 3 MeV. That's about 5 MeV. The bulk of solar neutrinos is coming from the PP flux, and Super K is, you can't see this flux of neutrinos. This is much, much higher. Again, that's 7 orders of magnitude higher.
And the total over all those is like 10 to the 10th
per centimeter squared per second.
Something like
Yes,
that. see them all.
Passing through us now, yeah. Okay. So the inverse beta decay process is actually quite interesting because this is actually the same method that was employed by Reines and Cohen to discover neutrinos in the late 1950s. An electron antineutrino interacts with a proton in the medium, and scintillator is mostly carbon and hydrogen from a physicist standpoint. Chemists would argue with that. When the antineutrino interacts with a proton, you get a positron plus a neutron. This positron quickly slows down and annihilates with an electron in the medium, giving these two gamma rays. And in the scintillator detector, what you're going to see is you're going to see this energy combined with this energy to give you the total energy of that particular event. The neutron then wanders around and with a mean capture time of 200 microseconds, finds another proton and gives a delayed signal. So there's a very clean signature for these types of events. And when you're looking for events that come every couple of days, it's very, very important to have a clean signature. And so the prompt energy is actually extremely well correlated with the neutrino energy for antineutrino energies of this scale. And so Camland, and I think Bob mentioned this actually in his introduction, can actually see the oscillatory behavior of neutrino oscillations. And that's because even though there are a lot of reactors where Camland sees the flux, almost all of the flux is actually coming from a relatively narrow band of distances at about 180 kilometers. And so simply by looking at the 1/E distribution of the antineutrino events, you can actually see the oscillatory behavior of neutrino oscillations imprinted on this spectrum.
So you have multiple sources, so your L is like a weighted average on the flux?
L is a weighted average on the flux, and it turns out that despite the fact that there are reactors all over the country, almost all of the unoscillated flux is coming from a relatively narrow band of L's, and that's why this works. Otherwise, it would be washed out. And so Camland measures the magnitude of this mass splitting very well, and solar neutrino measurements measure the mixing angle very well, and they also tell us the sign of that mass splitting. And so we actually, from these experiments, have learned quite a lot about neutrino oscillation. So oscillation experiments have measured all three mixing angles at this point, including a bunch of experiments that I'm not going to describe, the magnitude of the two mass splittings, and the sign of one of the splittings. And so what do we want to learn from now? We wish to learn the sign of the other mass splitting, and we want to understand this neutrino mass ordering and put limits on the absolute magnitude of masses of neutrinos. And this will be very nice when we get results from cosmology experiments that also put limits on the total mass of coming from neutrinos, and we can compare them and hopefully learn something about how the universe actually works. We further wish to explore whether or not neutrinos violate CP symmetry. For example, do muon neutrinos oscillate with electron neutrinos in the same way as muon antineutrinos and electron antineutrinos? So the two mass orderings that we have, we know the sign of the smaller mass ordering, the solar mass ordering. We don't know the sign of the atmospheric splitting, which is much, much larger. And so we could have a situation where we have a very hierarchical set of masses for neutrinos, where the lightest mass is very small, there's a slightly heavier one, and then there's one that's much more massive. Or we could have a scenario where there's one light mass and two masses that are quasi-degenerate here. And so understanding what that splitting is kind of the goal for the next set of oscillation measurements, and the next generation oscillation experiment is DUNE. And DUNE is an experiment that will be carried out in the United States. The program consists of an intense broadband neutrino beam at Fermilab, and this neutrino beam is aimed at western South Dakota at a large underground detector at the Sanford Underground Research Facility. And there are near detector systems that are located at Fermilab to measure the spectrum and the flux, as well as a very large underground detector that measures the spectrum and the flux after 1,300 kilometers. So when constructed, this experiment will have the longest man-made baseline of any neutrino experiment. For people who have seen the experiment name as LB&E in the past, this is a very recent change. We are now the Deep Underground Neutrino Experiment. But a lot of plots that you'll see in this talk were actually produced by the LBNE collaboration, and we've only very recently switched the name and elected new co-spokespeople. So this is the, this is a munch slide of the long baseline, the LBNE collaboration. That's supposed to show you about 550 names. And here is the motivation for this experiment. So these plots are relatively complicated, so I'd like to take a little bit of time going through them. These plots are the electron neutrino appearance probability for conversion from a muon type neutrino to an electron type neutrino. And on this axis is the neutrino energy in GeV. This is 1 and this is 10, so this is a log scale. And on this axis is the baseline. And this line is at 1,300 kilometers. That is where we plan to do this particular experiment. And the shade here is proportional to the appearance probability. So the darker shade, a darker shade means a higher conversion probability, and no color or white means very small probability. So let's look at these left plots to start with. So for the normal mass ordering, this is what the appearance spectra look like for neutrinos and for antineutrinos. So you see that in neutrinos, at say for example the first oscillation maximum, there's a relatively strong electron neutrino appearance signal, whereas for antineutrinos there's a relatively weak electron antineutrino appearance signal. And that's for the normal mass ordering. For the inverted mass ordering, one sees the reverse. And so there's very little appearance probability for neutrinos and a much higher appearance probability for antineutrinos. And what that means is if we design an experiment, when we design our experiment to be at this baseline, that we should have a very good chance of understanding what the neutrino mass ordering actually is. On the right side are similar plots. Again, on this axis we have the neutrino energy. This is 1 GeV, this is 10 GeV. But down here is actually now the appearance probability. And there are 3 different colors, and they represent 3 different values of the CP violating parameter. So for CP, delta CP of equal to 0, that is there's no CP violation, you get the red curve. For delta CP equals pi over 2, you get the green curve. And for minus pi over 2, you get the blue curve. Okay, and again, this is for the normal mass ordering, this is for neutrinos, and this is for antineutrinos. And so you see that there are actually very different appearance probabilities depending on what the value of this delta CP parameter is. It's related to CP violation. In addition, if you look very closely, you'll actually see that the peak positions here are actually different. That is, the shape of the appearance spectra are actually different depending on what this value of the delta CP parameter is. So this again is for the normal mass ordering, and this is for the inverted mass ordering, where you see very large changes due to the mass ordering in the absolute probabilities, and you also see pretty significant shifts in the spectral dependence of where these conversion probabilities occur.
What's the relative strength of the solar term? Which looks like it's not interesting.
Yes, so the solar term here starts to turn on at much lower neutrino energies, and in the beam that we're building, there's almost no flux there. So we're not going to be able to see much impact from the.
Well, that's what you want.
Right.
Yeah.
Right. So, but you see that there's a very rich phenomenology that we wish to study here in neutrino oscillation physics. So what's the basic layout of the experiment? There's a proton beam that impinges on a target that's in a target and what's called a horn system. This is basically a pulsed magnet. And this magnet will preferentially focus either positively charged particles or negatively charged particles down a decay region that's about 200 meters long. And so one can change what particles get focused by changing the polarity with which one pulses this magnet. And so again, this is actually, if you remember, the same decay mode that produced the atmospheric neutrinos as well. So it's the same reaction, just using a man-made proton beam. So it's pi plus goes to mu plus plus a muon neutrino, and if you switch the polarity here, so you preferentially focus negative pions, you'll get an anti-neutrino beam. And so a few hundred meters downstream from this, you'll actually have a near neutrino detector hall, and then 1,300 kilometers later, we'll have the far detector, which is a liquid argon TPC. So what this looks like on the Fermilab site, this is the main injector. So the protons will be pulled out of the main injector, sent to a target station. This is the decay region. This is the absorber complex, and the near neutrino detector hall will be built very close to the site boundary, and this is people's houses. So it really is quite close to
Just rent one of those houses.
So going piece by piece, now the protons are coming in this way. This is a little bit more detail about what these, again, these horns, these pulsed magnets look like. This is the target sitting in here, and this is focusing positively charged pions down this decay region. Again, this is a couple hundred meters long, and then there's an absorber here to stop any hadrons from getting into the ground. So the near detector complex actually consists of two different types of systems. So now we're looking at protons coming from this side. We're actually going to build a small hill on the Fermilab site. And it turns out to be more cost-effective. Quite likely. Just put a little statue on top of it or something. It turns out to be a cost-effective way to build this beamline, to build this small hill. And the reason is the target station, this is soil here, and this is rock below here. And so the idea is this decay region is really quite a massive structure. This is 4 meters in diameter, and then beyond that there's several meters of concrete. And so there's a lot of excavation that has to take place here. And then one would like to use the rock for its structural content for this very large target hall, absorber hall that's located here. And so it actually turns out to be cheaper to build this little hill than trying to build everything in the rock underground. And so the protons come here, they interact with the target in this location, and the pions decay here, creating the neutrino beam. Any hadrons, leftover hadrons, get stopped in this absorber hall. There's a lot more Earth, and then there's the near detector hall. You'll notice that this is at an angle, and that's because the Earth is roughly spherical, and we want the beam to actually come out in western South Dakota. I have to say this angle is actually exaggerated. The true angle is around 6 degrees, but hopefully you get the idea.
I hope you didn't give that one to the construction company.
We better double check that.
Right.
So we have planned detector systems that will detect the muons that actually pass through the absorber. So there's a big hadron absorber, but most of the muons actually make it through that absorber. And because the muons come from the same decay as the neutrinos, by monitoring the flux of muons, we actually can get a spill-by-spill understanding of the characterization of the neutrino beam. And so we have 3 types of detectors that are contemplated. There are arrays of ionization chambers, and this will give basically a profile that is a profile as a function of distance from the centroid of the beam on a spill-by-spill basis. It'll also help us make sure that we're actually pointed towards western South Dakota and not say Davis. And then further, we'd like to actually understand the energy content of these muons, again, because by understanding the kinetic energy of these muons, we actually can then reconstruct and constrain the energy distribution of the neutrinos. And so there are 2 different detector systems that are envisioned for this. Some threshold Cherenkov detectors, and so one can evacuate these detectors or put in a high-pressure gas or anything in between to change the threshold, the Cherenkov threshold, and thereby get some information on the kinetic energy content of the muons. One can, and then also some detectors that are located in various thicknesses of absorber material. And so muons that stop here had less energy than those that stop here, and have further less energy than those that stopped here, etc. And so by measuring muons that stop at a given depth in absorbing material, one is also then constraining the kinematics of the beam. There's a near neutrino detector, of course, that's contemplated. This design has been developed jointly between the US and India. It's a high-precision straw tube tracker that will have embedded high-pressure argon gas targets as well as some other nuclear targets. This detector is expected to be largely built in India. And right now the design is really quite large. This may change with time. But this scale is, this straw tube tracker is 3.5 meters on the side and about 8 meters in length. And this is, there's an electromagnetic calorimeter. There are muon identification systems that are interleaved in this very large magnet. And this is, in fact, a very large dipole magnet. And the philosophy here is to make high precision, high statistics measurements of neutrino interactions with argon, again, which is the far detector nucleus, and to make inclusive and exclusive cross-section measurements to build in constrained models to predict the event signatures at the far side and correlate them with the true neutrino energy. And one of the nice features about this detector is because it's a straw tube tracker, it has a very low average density. And that means that with the magnet, not only can we do studies of muons, mu minuses and mu pluses, and therefore muon neutrinos and antineutrinos separately, we can also separate electron neutrino events using the magnetic field. Electron neutrino events from electron antineutrino events. And so, and as we move forward, this actually could be coupled to a small liquid or gas argon TPC or some other technology. And one of the visions of that is here. This is a schematic of what the underground hull looks like. I remind you, this is about 5 meters here, and this is a relatively small liquid argon TPC. So the far detector is really quite beautiful. It's a liquid argon TPC, and my graphic is unfortunately doesn't seem to be working. But the idea is that a neutrino interaction will create charged particles in the medium, and there's an electric field throughout this large volume of liquid argon, which means that when you create a charged track, the electrons are going to start to drift, and in fact, they start to drift towards anode wire planes where they're actually detected, and that then gives a 3D image of this track that was created by a neutrino interaction, which can then be analyzed. And a simulation of some of these tracks is here. This is a simulation of a charged current electron event that has the electron and it has a high DEDX proton here. And this is a simulation of a muon event. And you can see, again, similar to the Water-Cherenkov detector, but quite clearly in this tracking detector, you can see that there's a very clear difference between muon-type events and electron-type events. And since we're trying to do flavor studies with muon neutrinos and electron neutrinos, this is clearly a very potentially beautiful tool.
It's a hefty voltage across the whole tank, I guess.
Yes, indeed it is. It's 500 volts per centimeter, and the drifts we're talking about are on the order of a couple of meters. So it's a very significant voltage. Creating the high voltage feed-throughs to handle that has been an active area of R&D. So this is one schematic of the 40 kiloton far detector. It would be located again in South Dakota. The scheme, frankly, now we expect to, instead of having 2 20 kiloton detectors, we now expect to have 4 10 kiloton detectors that allows us to do appropriate phasing based on what we expect to be the available funding. But this detector uses a very interesting cryostat design. It's a design that comes from the liquid natural gas industry, which is called a membrane cryostat. And a membrane cryostat is a very, very thick piece of stainless steel. It's got a characteristic size, so that characteristic shape, so that when you put cryogenic fluids in here and everything starts to contract, that the membrane itself can actually contract without ripping open. And then there's a lot of insulating material underneath. So the insulation for this type of cryostat is actually passive. And underground, that's a very nice feature. Instead of trying to have a evacuated cryostat, we can hold in something like 40 or 50 kilotons of liquid argon. And so in general, they outfit ships with this to carry liquid natural gas, and this has now been tested for our purposes for liquid argon, and it actually works quite well. There's a photon detection system. So again, even with the 500 volt per centimeter electric field, the drift time of the electrons is really quite slow. So in particle physics, 2.2 milliseconds might as well be forever. And so, so we have, in addition to the charge that's drifting, there's actually scintillation light that's produced. The time scale for this scintillation light, the prompt light, is on the order of 6 nanoseconds, so this is a lot faster. For beam events, this is not a big deal. The beam spill is about 20 microseconds long, so we'll know where to look for neutrino interactions in this spill. This is a lot shorter than the actual drift time. But for non-beam events, the interaction time will not be known unless we use the light to figure out what that time is. And so there's a couple of schemes for detecting the scintillation light that fit with that can be integrated with the time projection chamber.
How many events per burst are you looking at? Oh, it's
Sorry. Talk might be a little shorter than I anticipated.
Time for a review.
Right, okay. Okay. Great, thanks. What was your
How
question?
many events per bunch? Like, do you have to worry about pileup or anything like that?
At the near detector, there's significant pileup. At the far detector, no, that's not an issue at all,
So
unfortunately.
Each bunch you get like a fraction of an event, basically.
Yes,
Yeah.
yes, it's well below a percent of the spills will have a neutrino interaction in them. At the near side, on the other hand, the rate is quite large. It's about 0.1 events per spill per ton of material for neutrino interactions. In addition to that, there are a lot of muons that are generated upstream in the rock that will also pass through the detector during the spill. So, okay, let me quickly go through some of the physics results that we anticipate. These are the electron neutrino and electron antineutrino simulated spectra. And these spectra are simulated. This is for no CP violation. This is for delta CP equal to pi over 2, and delta CP equal to minus pi over 2 for the normal and the inverted mass ordering. And that leads to sensitivity plots that look like this. For the mass ordering, if the mass ordering is normal, we would expect after 10 years of running to basically be at or above 5 sigma in terms of the determination of a mass hierarchy. Again, this would be for the normal ordering, and this is for the inverted ordering. And then our CP violation sensitivity is also well above 5 sigma for several broad ranges of this delta CP parameter. You can see, of course, that obviously the sensitivity gets much worse when there's very little CP violation to actually measure. So there's some challenges to measuring CP violation, and that is that DUNE, what the experiment really needs to produce is a conversion probability of muon neutrinos to electron neutrinos as a function of neutrino energy, and a conversion probability of muon antineutrinos to electron antineutrinos as a function of antineutrino energy. And DUNE does this by using this broadband neutrino beam and by passing this neutrino beam through matter. And so there's actually a built-in CP asymmetry in the experiment. And so if we want to measure CP violation, we have to know what the standard model CP asymmetry of the experiment is. It's a very, very critical piece. Oscillation phenomena depend on the mixing angles, the masses, and of course they depend on the neutrino energy. So we really need to understand, but the neutrinos, when they interact in the far detector, don't come with a tag that tells us what their neutrino energy was. So in order to understand what that neutrino energy is, we have to go reconstruct it. And so it's very, very important to understand the correlation between true and reconstructed neutrino energy, and especially any differences between neutrinos and antineutrinos. And so for a charge current muon neutrino interaction, one gets the charged lepton, and then one has a hadronic system. And this hadronic system will have particles that we should measure very well, and we'll also have particles that we don't measure very well at all, and those are neutrons. And one of the challenges for us, because the cross-sections and the final state interactions are very poorly known in the energy regime where we're going to do this experiment, we actually don't have good predictions for what these neutron spectra ought to look like. When we do look at what we know about them, what we actually find, if you look at the right plot, is that the energy that goes into neutrons from neutrino interactions looks very different from the energy that goes into neutrons from antineutrino interactions. And so we actually need to understand the detector's response to neutrons. And that is one of the reasons that we've decided to build the Captain detector and put this detector actually in a neutron beam. So this is our cartoon of the Captain detector. It's 1 meter high, 2 meters in diameter. It's actually a hexagon up here. It's a hexagonal TPC. The drift is actually in the vertical direction. It's got 2,000 channels, 3 millimeter pitch, and this total is about 5 instrumented tons. And this detector is actually portable. It's got an indium seal, and so it can be opened and closed, and it can be moved to various facilities to make interesting measurements. And I note that the photon detection system is actually a Davis responsibility. And so we're very fortunate to have Davis involved in this experiment. It's got a laser calibration system and cold front-end electronics, and the physics program for this detector is actually focused on the challenges to DUNE. And so one of the first things that we want to do is actually carry out some neutron running to help us understand the neutron response in liquid argon TPCs that, again, is not very well constrained by models. So this is the collaboration, and this is the UC Davis contingent. And so I think I am basically out of time at this point. So why don't I skip and conclude. So the DUNE experiment has an exciting and diverse physics program enabled by a strong international partnership. The beam neutrino physics probes the neutrino mass hierarchy and leptonic CP violation. The highly capable near neutrino detector enables the neutrino oscillation program. It also has a high precision neutrino interaction program of its own. The FAR detector enables measurements, for example, of supernova and atmospheric neutrinos in addition to the beam physics that it will do. And we're building this Captain detector, this 5 instrumented tons of liquid argon TPC at LANL. And this program actually is designed to address several scientific questions of importance to DUNE. And you saw, in particular with the neutron running, that this is a very critical piece for us to make sure that when we do stand up and tell the world we've discovered CP violation with DUNE, that we actually get it right. Thanks very much.
So we have a lot of questions, but maybe some more out here.
Okay, I have a conceptual question. First, thank you for a very clear presentation. The conceptual comment is the following. The value of delta is parameterization dependent of the 3x3 mixing matrix.
Yes.
Comment 1. And so my assumption is probably you're using the particle data group 1.
Yes.
If so, then that's my and Kuhn's parameterization.
Oh.
Physical review letters, 1980s. And we did that. One thing, particle data group, I haven't yet to convince them, I haven't communicated them. They should use our product. It's a product of 3 matrices. Each one corresponds to one neutrino experiment. We just sort of did it by, fiat. And it turned out there is a deep mathematical reason for that, and which I have a physics letter paper 2007 to clarify that, actually, n by n. So keep on going. If there are n generations, I have the parameterization for you.
Well, we'll keep looking. looking for more generations as well.
So,
Yes.
so therefore, what I want to say is, even your delta is big, does not mean CP violation is big yet, because it is a product of the sine theta 1, 2, sine theta 1, 3, sine theta 2, 3 times sine delta. That is the one which is parameterization free for CP violation, and the credit should go to, actually, to myself and let me see, the lady physicist from Norway. Cecilia, right. I had a pre-run in that physical review letters. We call that XCP. She calls that JCP. Okay,
Yes.
but she deserved that because she related that to the mass matrices, which I did not make that connection. But that's great. Okay.
Thanks. No, thank you very much for that.
Okay, so thank you.
I think I have a related question. So I assume therefore that there is probably some covariance between the CP signal and the hierarchy signal in your experiment.
Yes.
So if the hierarchy was narrowed down by cosmological observations, that could narrow
Absolutely.
your sigma for the CP.
Yes, absolutely. I don't have the plots with me to show that, but we have looked at scenarios, for example, what if you do know the hierarchy?
Yeah.
Then what does the CP sensitivity look like? And yes, it's of course much better. And in fact, for example, an experiment like T-decay, especially an experiment expanded for T-decay that includes a hyperconic on a very large detector, tells us very little about the hierarchy from the beam physics. Actually, could tell us something from the atmospheric neutrino physics. But if the hierarchy were known, one can actually learn a lot about CP violation looking at that experiment, even though it does not have sensitivity to the mass hierarchy.
So obviously, the neutrinos produced in Fermilab are the primary science goal, but I know one of the reasons for going underground is to have sensitivity to supernova.
Yes.
And is there any sensitivity to solar neutrinos that would be interesting? Or is there any other new physics out of solar neutrinos that you...
I think there is certainly interesting solar neutrino physics to do. I don't think it will be done with this detector. But I think especially a lot of the very interesting solar neutrino physics to do is looking actually at the very low energy part of the spectrum, the DP in particular, which of course this detector will.
What's your threshold?
I'm sorry?
The threshold is going to be...
The threshold, so,
I mean,
is under, so call it 6 MeV. I mean, on a good day.
So I'm wondering what governs basically the neutrino beam profile, as a propagates away from Fermilab. So presumably the charged particles you have a very good handle on. You could shoot those straight at South Dakota if you wanted, right? If you had the pipe to do it.
Right.
But now it gets spread out into neutrinos. What's the limiting factor with focusing that better, toward South Dakota or?
Right, so it's there is an interplay in the design of the beam line, which I think is, why does the beam line look the way that it does?
Yeah.
Because that's obviously, what we're trying to do is we're trying to maximize the flux in a particular range of neutrino energies. And we'd like to minimize the flux in ranges of neutrino energies, particularly higher neutrino energies that could cause background in the lower neutrino energies, if possible. And so the beam pipe is actually 4 meters in diameter. It's a very large beam pipe. Again, because we're really kind of more interested. Oh, and it also is correlated with what the primary proton energy is. So frankly, for this experiment, we would love to operate at, say, 20 20 to 30 GeV primary proton energy. The problem is the main injector, the power starts to drop off below, and there's some debate about this, but somewhere between 60 and 80 GeV, the power is actually starting to drop. And so we can go, the nominal running energy for the main injector is about 120 GeV. We can certainly go down to 80 without taking a power hit. And we may be able to get down close to 60 without taking a power hit. So based on the primary proton energy, our expected ability to operate horns at a particular current, distance, those are kind of all the parameters that then get tuned. And so, but it is, you have a pion decay, and that pion decay gives us, I mean, look, there is a flux, there is a backward flux. It's pretty small, but there is even a backward flux of neutrinos. So there are certainly neutrinos, a neutrino flux that actually is essentially 4 pi from this beam. Obviously, it's quite focused. And then you can say, well, how do you characterize how well focused it is? So one study that was done in one of the earlier incarnations of the experiment, there was a question about maybe starting the experiment with the fire detector on the surface if funding was limited, and then later moving underground. And then the question is, well, if you build a beam line, you're not going to turn the beam line. You know, can you tolerate that? Can you because that's about a mile.
Yes.
Top to bottom. Studies were done, and the flux and spectra were not significantly different, top to bottom at 1,300 kilometers, which gives you a little bit of a flavor. But 10 miles, you probably would see some small spectral changes. And you'd start to see a real drop off in flux once you get farther away.
We have one more question. If not, let's thank Mr.